Hello everyone, my name is Stefan Liu. I'm a PhD student at the Cyber-Physical Systems Lab of Matthias Althoff at the Technical University of Munich. In this video, I will present our paper on how modular robots can be used to optimize performance in automation and analyze how high the potential improvement is compared to standard industrial robots. When it comes to the application of modular robots, three main advantages come into mind. The first is that modular robots can be flexibly reconfigured, which comes in handy if robot tasks are frequently changing. Secondly, modular robots can be easily repaired by replacing broken modules. Third, by mass-producing standard modules, the cost can be reduced. On the right-hand side, you can see the modular system Pro Modular 1 that has been developed in our lab for industrial applications, which we subsequently use in this study. In this paper, we are going to address the question how to find the most optimal set of modules suited to a given task. We hereby focus on industrial applications, where the mass customization trend is a big driver for flexible automation solutions. By flexible, we mean that the environment is frequently changing, as well as the task for the robot. Additionally, industrial applications require high-performing robots. Classical solutions, such as the welding robots on the right, are highly performant but cannot adapt very well to changing tasks and environments. In this paper, we are, however, going to show that not only is our Pro Modular 1 robot adaptable, but can also deliver higher performances than standard industrial robots when optimized. When looking at robots in industrial applications, we mainly regard the following three task types. First, the task can be a trajectory in task space. Examples here are welding, dispensing, or part processing. Secondly, the task can be a list of poses. Examples are parts handling, machine tooling, assembly, or the spot welding task from the previous slide. If no path is available, one can also do a workspace optimization, which we do not go into detail in this video. Performance parameters we evaluate include the cycle time, which is the time the robot needs to perform a task, and the energy consumption, which are both costs to minimize. Furthermore, we make sure that the task is reachable. The motors are capable of handling the forces and that we do not hit obstacles along the way. For the sake of brevity, we do not regard repeatability, manipulability, etc., but the optimization framework allows for straightforward extensions to the cost function. Moving on, we first address how we find the most optimal composition. Here, we want to highlight two contributions that our paper provides to the community, both addressing the computational feasibility of the optimization. The first main idea is to restrict the enumeration of possible module compositions to common industrial kinematics. We highlight four examples, which are 6 degrees of freedom's PUMA, elbow, and ETL kinematics, and the 7 degrees of freedom DLR kinematics. We categorize the modules into generic categories, from which all of these and more standard kinematics can be built. The rationale behind this idea is that the popularity of these kinematics serve as a heuristic. The second idea is to use a hierarchical elimination approach through efficient constraint checking, meaning that we first evaluate constraints that are efficient to compute, such as analyzing the feasibility of selected poses first, before checking the feasibility of the entire trajectory. We check the reachability using inverse kinematics, gravity forces using the Newton-Euler algorithm, and collision using the flexible collision library. To generate collision-free trajectories, we use RRT-Connect and subsequently simulate the robot dynamics using the Newton-Euler algorithm. If any of these feasibility checks fail, the composition is instantly eliminated and the cost is not computed. The algorithm for all the task types can be found in the paper. We now show how our Modular 1 robot developed in our lab compares with commercially available robots, such as the Schunk LWA4P, the KUKA LWR4 Plus, and the Stäubli TX90. The comparison is done by simulating the robots, where we compute the cost of cycle time and energy. More than 2,000 random paths have been generated with random payloads between 0 and 50 Newton. We perform a one-to-one comparison, meaning that a task must be feasible for the commercial robot, so that we are able to obtain the performance improvements using optimized modular robots for each task. The graph on the right shows how often a kinematics has been chosen for the optimal modular robot. You can see here that the DLR is favored because of its additional redundant axis that allows more room for optimization. The elbow kinematics, however, is almost never chosen. From all the experiments, we will show select ones here. At first, we look at fixed task space trajectories, such as in dispensing tasks. We observe that the modular robot consistently finds compositions that has more energy efficient movements than the commercial robot, although the end effector is tracking the exact same trajectory. Next, we look at tasks where the robot should move as fast as possible between predefined poses, such as in parts handling. Again, the modular robot consistently finds compositions that are more time efficient and energy efficient. Suitable kinematics are found, such that movements between poses are reduced. At last, we look at tasks with obstacles, such as tooling for a milling machine, where we also have consistent time and energy savings. However, due to the constrained environment, the direct improvements of the modular robot are less than the obstacle-free case. When comparing paths at different lengths, we also observe reduced improvements for longer tasks. Here we show a summary of the savings in percent. More detailed numbers are in the paper. The main takeaways of this comparison study is that our Modular 1 robot is capable of doing the tasks of all 3 commercial robots. Also, the Modular 1 performs better in direct comparison. Performance improvements are, however, reduced when a task has more constraints, such as when the task space trajectory is fixed, as can be seen above, or when the obstacles are introduced, or longer trajectories are compared. An interesting point is that the Stäubli TX90 robot is not very energy efficient, although it is in the same payload class, but it has a stiffer design that possibly leads to a high accuracy, a factor not regarded in this comparison study. To summarize, we presented an optimization based on the enumeration of standard kinematics and a hierarchical elimination that considers the kinematics, dynamics, and the geometry of the robot, while being computationally feasible. This framework can be easily extended with other manipulator kinematics, such as ICRA, but has the disadvantage that non-standard kinematics are omitted. In a comparison of modular robots with commercial ones, we found that our Modular 1 robot is adaptable to the tasks of all 3 compared commercial robots, and usually performs better. The same conclusion goes for workspace optimization, which we did not cover in this presentation. In the future, we plan to also include repeatability as a criteria, which is also important for industrial applications. We also want to validate our approach and computations with real experiments. Computation time can be further improved using global optimization methods such as genetic algorithms instead of the brute force evaluation here. Thank you for watching. I will be very happy to answer questions, either via email or Slack.